Okay, so hello everyone, welcome to another video. And today we are jumping off the plan and we are basically discussing this Leetcode daily challenge problem for today, 9th of Feb. It is jump game 2. Okay, so first of all, we'll try to understand the problem and then we'll try to come up with an approach to solve this problem. Okay, it has been asked in Amazon, Apple, Google, Microsoft, so it's pretty common problem actually. Okay, so let's get started. Uh, you're given a zero indexed array. That's fine because in Java you anyway have zero indexed array of integers nums of length n. You are initially positioned at nums 0. Okay, initially you are at the very first element. Each element nums I represent the maximum length of a forward jump from length of from index I. What it is saying is if you are at index 0 and it contains value 2, it means you can jump to these two elements from this index. That's what it is saying. In other words, if you are at nums I, you can jump to any nums I plus j, where j is within the limits and I plus j is less than n. Okay, yeah, that's clear. Return the minimum number of jumps to reach. So what these 2 points are saying is basically this thing only. So if it says 2, you can reach these two elements. At the same times, no jump will carry forward you beyond the last element. So that's these two statements are trying to say. Return the minimum number of jumps to reach the last element, basically. The test cases are generated such that you can reach the last element. Okay. So let's try to visualize the problem. Okay. Let me open the whiteboard. And I'll take the first example, which is 2, 3, 1, 1, and 4. So we start from this element and we have to reach this element, last one. And we have to find the minimum jumps required to reach n minus 1. So using this minimum term, the first approach that will be coming into your mind is the DP one. So I was also trying to come up with a DP solution, but it is the complexity is higher actually in that case because you have to keep track of whether a particular index is reachable from a certain previous index or not. Uh, so we'll try to discuss a better solution, which is using the greedy approach. In greedy, you might be knowing that we make the most optimal choice possible, okay, for to reach the final solution. So if you look at it, if we start from index 0, we will always start from index 0. Let's look at the element here. It says 2. So it says you can basically reach 3 and 1 from this position. In other words, the number of jumps required to reach these two elements is 1. So if we had an index like this, if we have an array like this, which stores the minimum jumps, it would look something like this. We'll discuss for the rest, but it will look something like this. Minimum jumps required to reach these two elements is 1. So we'll store that. Now, if we look at the jumps possible from these two indexes, It can jump 3, so it can jump till last. It can jump 1, so it can reach till here. So basically, from these two, we can jump to 1 and 4, okay? And jumps required will be now 2. 1 to reach them, and 1 to reach from them to 1 and 4. So our minimum jumps array would start looking like this. Sorry, there are only 5 elements, so this is not required. 2 and 2. At the end, we just need to return uh, the values, okay? For example, in this case, it will be 2. This will be the answer. Let's take another example to see this approach. 23014. Okay. The optimization that we are doing is we will be optimizing for each, for example, for this jump, these two elements are possible. So we will make the best possible use uh, to calculate the number of jumps possible. So for example, in this case, it is for both of these elements, it is 1. Okay, it doesn't matter which one you are taking to jump to these two. Uh, sorry. So to reach 3 and 1, the number of jumps will always be 1 because these two elements are reachable from 2. Similarly, these two elements are reachable from 3 and 1. So it will always be number of jumps will be 2 because you have to go through these elements for sure to reach these two. Okay, let's take another example so it will be more clear to us. Where is this? Okay, number of jumps required to reach index 0 is again 0 because we are already standing there. But we can reach these two elements from this. Jumps became 1. Now from these two, what all can we reach? From this one it is 0, so we cannot reach anywhere. Okay. And when I say reach, I am talking about the elements after this because obviously we have reached these two elements, so we can reach these two. So for example, for 0, it is possible to reach 0, right? Because we are not moving. But for this one, we can reach these two from 3. Okay. So jumps will become 2 here. And if I create the corresponding minimum jumps array, it will look something like this. Let's see the answer. Yeah, it's 2 only. So if we try to code it up on the side, let's see. Okay. Uh, where is my cursor? Public int jump. Okay. Public int jumps and an integer array that has been given to us. So how to approach this problem? Okay. First of all, let's have the variables out of the way. And this will store the result. it will be 0 initially. Okay, so now if we take the example of first element, we see that 3, I'm talking about this example, 3 comma 1, 3 and 1 are possible to be reached by first element. Similarly, these two. So we need a variable to store what is the furthest distance possible to reach with a certain ith value. So for example, this is I equal to 0. What is the furthest distance possible to reach using this? We need to store it because we will need to update the number of jumps for these two elements in the minimum jumps. Okay. Uh, we won't be initializing this because it's not required to be done to do that, but we'll try to do this. Or should we do it? Mm, it's not required actually, yeah. So 3 comma 1 is reachable from 2. So what is the furthest distance possible to be reached by index I equal to 0? It is for in this example, it is nums I plus I. Okay. So in this case, it is 0 plus nums of 0 is 2. So it is 2. And similarly here, what is the furthest distance possible to be reached with, let's say, 3? It is nums I, which is 3, plus the index 0, comma 1. Okay. So it is 3 plus 1 is equal to 4. 0, 1, 2, 3, 4. So the last one is the furthest one. So we will need to do something like nums I plus I. Okay. And we need a current furthest variable that is possible to be reached. This is important. We'll come to that. And what we also need is we need a variable to store what is the basically the jumps required at a certain ith value. So we will need to store um, the jumps required. Okay, in this case, let's call it jumps. It is more clear then. So we will keep updating this as and when we reach these values. So for example, if you reach I equal to 1 or I equal to 2, you will update the minimum, sorry, jumps required accordingly here. Okay. So what you need to do is you need to first of all write a loop, obviously, starting from 0 and here wait. So you don't need to go all the way to n minus 1. Why? Because if you are jumping to from any of the, where is my cursor? If you're jumping from any of the previous values, that jump is already accounted for, right? You have reached the n last element. So you do not need to process what all elements are reachable from the last index. Okay, that is why we will go only till n minus 1 because I equal to n, sorry, I equal to n minus 1 is the last element that we need to reach. But we don't need to calculate what all further indexes are reachable from the last index. Okay, so that is why we will have only till n minus 2. I. I will go only till n minus 2. So, what we need to do is, in every step, we need to update our current furthest. Okay, just a minute. And we will use nums I plus I. Okay, here. Now let's understand this first. Okay, let me decrease the size. Yes. So, initially I was 0. Okay, so what what is the current furthest that is reaching? So current furthest is already like initialized to 0 because we don't know, we haven't processed I equal to 0 yet. So that's why the current furthest is 0 for initial. Now when we come to I equal to 0, nums I plus 0. Okay, so it is nums I only. What is the first value? It is 2. What is the current furthest possible? In this case it will be 2. Index 2 is the furthest possible index to be reached by num0. Okay, so this index will help us uh, calculate and store, basically have these values for each index stored. So for till I equal to 2, we will we will store the index, sorry, the number of jumps as 1. So we need another variable. Let's call it current end, because we are naming it like this because it is for a random ith jump, it is the last element. Okay, last element. So we are keeping store of that. Let's call it 0 only. Where is my cursor? Sorry. Current end. Okay. Now, if at any point we reach the current index, sorry, current end, we have to update the jump value accordingly. Okay. So if I is current end, jumps should be incremented first of all. Second of all, current end should be updated with the current furthest value. Now let's try to understand this step for I equal to 0. For I equal to 0, we knew that current furthest is the index 2 and current end was 0. Okay, so initially it will be I equal to 0. So jump will become 1. What this means is as soon as you cross I equal to 0, number of jumps for any element after this will become at least greater than or equal to 1. So if I equal to 0, um, as soon as you cross this ith index equal to 0, you will have jumps greater than or equal to 1. You can see it here. Okay, that is why we are starting with current in end and current furthest values as 0. Okay, because this will help us store the accurate jump value possible. Okay, and why we are updating the current index, current end, sorry, current end is required to be updated because uh, now once you cross this index, which is I equal to 2, this will so I equal to 3 will be compared has to be compared with the new value of current end. If we don't update current end, it will still show, for example, 0, and it will not go into this if statement at all. It will not be able to update the number of jumps possible for that. So we need to update our current end possible with the current furthest. So let me clear this out, and we will do one iteration, and we'll take an example, that one only. 23114. Okay. 23114. So initially I was here, sorry, let me call this jumps and current furthest and current end. Okay. Now for I equal to 0, okay, initially all of them were 0. Now for I equal to 0, what will happen? Current furthest will become uh, this one. I equal to 2 is the maximum that you can reach with if you are standing at I equal to 0. So this will become 2. Current end, it will now go into this I equal to current end. So this will be true, okay, for I equal to 0. Jumps will become, sorry, 1, and current end will become 2. As soon as you cross this I equal to 0. I equal to 1. Now the current furthest, what will be the current furthest possible? It will be nums I, which is 3, plus 1, which is 4. Okay, this is the furthest possible. If I is equal to current end, so it will not go in this case. For I equal to 1, it will not go here because I is 1. Current end is 2. It will not go into this if statement here. So this will remain 2. So jumps will remain 1. What this means is to to cross I equal to 1, even if you cross I equal to 1, there is a certain element which is 1, which is still having the jumps equal to 1. Even if you cross it, jumps is 1 for the next element. Let's go on. I equal to 3 and I equal to 4, we won't go because we would have reached the final result possible, because you can only jump to the last element from a previous element, right? So that's why we are not processing the last element. Even if you look at here, I equal to n minus 1, it was because of that. Now for I equal to 2, what happens? Nums 2 plus 2. So nums 2 was 1, 1 plus 1, 2. 2 is the furthest. But current furthest is already 4. So it will remain 4. Okay, current furthest will remain 4. But I is now 2. And current index is also 2. So the jumps need to be incremented for the further elements after this one. So the jumps for these two will become 2. This is what is happening here. And current end needs to be updated. So it will become 4. Because what it says is now you are now in the window of this. That's why the current end is 4. Now for I equal to 3, nums 3 plus 3, 0, 1, 2, 3. It is 4. Okay, the furthest you can reach is 4, but we won't update it because current furthest is already 4. So 4 comma 4 out, what is the maximum value out of that? It is 4. I equal to current end. Current end is 4, but I is equal to 3. So current end will remain same and jumps will also remain same. Now this will be the final answer of number of jumps. So you just need to understand the approach that we take, okay? This one. This is the most critical part. For every index, we are trying to find what is the range of elements that are possible to be visited by that jump. So if you make jump from index equal to I equal to 0, we can jump to 3 and 1. So we need to make sure it's as if you were having a minimum jumps array and you are storing the number of jumps possible to reach that. So it's similar to that. Okay. So for 2, you can jump to these two elements. So the minimum jumps for the both of them will be 1, and so on. The last the last value will give you the answer, final answer, number of jumps required to be reached to the last element. So hopefully that was clear. And time and space complexity, we are only iterating it once, so it will be, if you look at the code, it is O of n. Space complexity is constant because we are not using any variable which varies with n. Um, so let's try to write the code for this. Okay, problem. Let's go back. Yes. First of all, let's store and initialize all the variables that we might need. We need n. We need current furthest. We need the current window end. Sorry, current jump range end. Okay, it's like that. And we need the number of jumps which will store the final answer. Now go from 0 to n minus 2 only, because again I have explained it, last element has to be reached by a jump. Okay, so there is no need to process the number of elements that are possible to be visited by this element. So because this is last one, we don't need to calculate what all indexes we can reach if we jump from this index. This index needs to be reached. Okay, that's why it is only going till n minus 2. Now current furthest will be math dot max of current furthest, comma, um, yeah, we had that formula, right? Nums I plus I. Again, to explain it, from current, for I equal to 0, we'll take the example. These two are possible to be reached. So how to calculate what all elements are possible to be reached? We calculate it using this thing. So num0 plus 0 will give us what all elements were, basically what is the furthest uh, index that can be reached from index I. Nums I plus I is the furthest index that can be reached from ith index. If you don't believe this solution, you can try it with some other value as well. You can try it with, let's say, I equal to 1. For I equal to 1, what is the furthest possible to be reached? It is 4. index 4. So nums 1 plus 1 is 3 plus 1, 4. So it is always correct. It will give you the what is the maximum range of a jump from a certain index I. Now we also need to compare and update our jumps accordingly. So if the I has reached the end of the jump, okay, for example, initially the first jump will happen as soon as you cross the zeroth index. You will have to jump. There is no solution that you won't jump. Okay, jump will at least be one as soon as you cross index 0. So once we are at index 0, we need to update the jumps accordingly. So jumps has to be incremented, and we also have to store the current end variable so that we can update our jumps accordingly. So when will the next jump occur? So we have to store this current furthest variable in this and update it. I will explain this again. Okay, but at least these two lines should be clear. As soon as we cross I equal to 0, at least we have to make one jump. So that's why the jumps needs to be incremented. Okay, and current end will take another jump example to understand this statement. Okay, let's take the jump that we will make from this jump. Okay, so 3 and 1 are both reachable from 2. Okay, so when is the next jump going to occur? It will occur as soon as we cross this one, because 2 can be reached from this, and as soon as we cross this one, there is at least two jumps required for any element further than this one, first one. So again, that is why we are incrementing jumps. But it will go only into this if statement if this current end is updated accordingly. So current end should store this index value, which is 2. It should store that. Otherwise, you won't be able to increment jumps properly. That is why current end was updated with the maximum jump possible for this one, this element. Okay. Uh, Let me current furthest. Let me do this thing as well, so it is more clear. Just like I did. Okay. So current furthest and all of them are 0 initially. You arrive at 0. What is the current furthest possible from this jump? It is 2. Okay. What is the number of jumps required for any element after I equal to 0? It is 1. So that is why it will go into this and it will update it 1. Okay. And current index needs to be updated for the next jump. So next jump will occur only when I crosses this value. So that is why we are storing this current end here. Hopefully that's clear. Now let's go to another jump. Um, okay, so we arrive at I equal to 1. I equal to 1, what is the maximum possible furthest position that we can reach? It is 4. But current end is 2, I is 1. It won't go into the if statement and it shouldn't because there is another 1 that we need to process. Okay, we need to find an element. So if this was not one, let's say if it was 4, okay, then we still need to process this value so as to calculate what is the furthest possible. Only then we can conclude what is the furthest possible uh, for this window. Okay. In this case, even the first element is able to give us the last index, the maximum that we can reach from after jumping from these two elements. So I will become 2, I equal to 2, and yeah, current furthest will not change because from first one we can maximally we can reach this one, second one. So jumps will remain. So now once we cross the I equal to 2 barrier, jumps has to become 2. Has to become. This is very critical to understand. Once we are at these two elements, for both of these elements, jumps are at least 2. It should at least be 2 according to the logic that we have done. And current end will need to be updated again because we have made a jump and we have to calculate when is the next jump going to occur, and we need to modify that accordingly according to the maximum window size possible, maximum jumps window possible. Okay, so in this case we will just update this to 4. Now we will reach this index I equal to it is 3. For I equal to 3, current furthest possible will remain 4 because that's anyway the last index, right? And jumps will remain same because current end is also 4. Sorry, I is equal to 3 and current end is 4, so it won't go into this. So jumps won't be updated, jumps will remain same. Similarly, so this is the last index that we have to process, right? So that's all I think. We will reach n minus 2 and this loop will be closed. And we will return the number of jumps that we made. If we run it, so it is accepted. Okay, good enough. So hopefully that was helpful and not too confusing because it requires some advanced greedy method here. Uh, it's not as straightforward. Okay, it's not the approach is intuitive, but to come up with the code, it is not as straightforward. So if you find it confusing, that's fine. But the approach should be very clear what we are trying to do, how we are making the jump, and what is the how we are using the fact that what is the furthest jump possible, and only then we are updating the number of jumps. So those should be clear. But it is a tricky question, I would say. Slightly tricky because the greedy method is working here. Uh, and it is if you go by the dynamic programming approach, I think you will have n square solution here, which will give you TLE for at least for the test cases they have included as a part of this problem. So that's all for this video. Hopefully this was helpful. Time complexity is let me add it here only. Okay. So I just wanted to save that information. So that's all for this video. Hopefully this was helpful. Let's meet in some other video.